Okay, consider an object in motion, and we measure the position of the object over time. So our object's moving, then we sit still for a minute, then we kind of slowly get moving again, then we speed up, and then we stop. And so when Newton was kind of figuring out the physics aspect of gravity and things, he noticed that mathematically it was difficult to kind of determine the instantaneous velocity or speed. So if we travel a certain distance over time, for example, I started at the point x1, y1, where x1 represents the number of time and y1 represents the position, and then I look at the final position and I calculate the distance between the two of them. I can figure out how far I travel, but what I'm really interested in is the slope of this, because the slope of this is the change in y, which is position, over the change in time. And that's what velocity is how far did we travel over how long it took us to travel it. And so as we look at the slope of this line, and that slope of that line represents the average speed, we could probably figure out a way to find, or we should probably observe, that the slope does not always match up with the slope of the curve. So this black line is the average speed or velocity of the red line. But if I wanted to know the speed at this particular point in time right here, well, what I would need to do is calculate another slope, because as you can see, the slope is steeper on the red line than it was on the original black line. So I can calculate a steeper slope by choosing two different points on the line and then calculating the slope of those 2 points. But here's a problem. What if I wanted to know the speed right where the green dot is? Well, if I wanted to know the speed right where the green dot is, I would have to maybe arbitrarily choose 2 points. Now, the 2 points that I choose have to be really close to the green dot, because if you notice, it's a horizontal line, and we all know from algebra that a horizontal line has a slope of 0. So what I want to do is I want to choose a dot or a point on the line that's really close to the point that I'm interested in. So I could choose 2 points, one to the left, one to the right of the dot, and if I were to calculate the slope between those 2 points, I would calculate a slope of 0. And so I'm drawing this horizontal line to represent the slope. Remember that a horizontal line has a slope of 0. So if I were to call the x-coordinate of that x, and I were to go over a little bit just to the right of x, and I'm not saying I'm not going to put a number to it, but just a little bit to the right of x and choose my second point, that should be sufficiently good enough to get a good approximation. And so what I'm going to do is I'm going to call the distance between x and that next point h, so the second point should be x plus h. Now the corresponding y values will be evaluated at f of x and f of x plus h. So I have 2 points where I'm going to calculate delta y over delta t, and I've used x's, so I'm going to interchange x and t a lot so that you guys can get familiar with the fact that the independent variable, it can be t or it could be x. But to calculate the y values, remember that the slope is the final y minus the initial y, and the final x minus the initial x. So my final y will be f of x plus h minus the initial y, which would be f of x, and likewise for the x's on bottom. So if I rewrite this on a cleaner screen, my final y would be y sub 2 minus y sub 1 over t sub 2 minus t sub 1. That's how we calculate slope. That's the instantaneous speed. But what I've done is I've arbitrarily chosen to write this in function notation by selecting t plus h, or f of t plus h, right, minus f of t, and then I'm going to choose x plus h minus x. So when I do that, if I say t plus h minus t, what I'm looking at is I'm looking at a function as opposed to plugging in numbers. So if I clean this up a little bit, I'm still going to get f of t plus h minus f of t, but the t's cancel, so that's all over h. Now, this could be the instantaneous speed evaluated at that specific point if I could make h equal 0. But we all know that I can't make h equal 0, because if I make h equal 0 on the bottom of the fraction, it'll be undefined. I can't get any information out of an undefined fraction. So I have to figure out a way to have h approach 0. And so one way that we can make h approach 0, in other words, what that means is I'm going to make, if I make h approach 0, my second x point will be very close to the initial x point, and that will give me a very precise measure of the slope between the 2 points, i.e. the velocity at that instant in time. Okay, so again, just to kind of recap, x plus h, right? And then when we simplify that, we get this formula. And so what I'm going to do then is, since I can't plug in h for 0, I'm going to let h approach 0. And I'm going to keep this in function notation. So the original function listed here, I don't know what that value is, but I'm going to allow that x plus h to approach 0. And so let me show you why we want h to approach 0. Let's assume that h is really big. Let's assume that h is really far away. If I choose a distance that's far away from the original point, I'll get a different slope. Here, I have a positive slope. But as I get closer to the original x, or as I allow h to equal 0, I get closer and closer to the original point, so my slope would swoop down, and that would give me the right answer. I'm going to over-exaggerate this concept with a really curvy curve. So let's apply the same concept here. X and f of x, if I wanted to find the slope of what we call the tangent line, it just touches the curve once. So if I arbitrarily choose what h is, here's an h that's far away. Well, the black line represents the instantaneous velocity if this was a graph of position over time. Well, what we see here is if I shorten my h, in other words, as h gets closer and closer to the original x, eventually I will get a line that's almost identical to the instantaneous velocity. In other words, if I let h approach 0, then what I'm going to end up with is the instantaneous velocity. So if I take f of x plus h minus f of x all over x plus h minus x, and we let h equal 0, but we can't, because when we simplify this, I'm going to get some funny business, and I'll have like 0 over 0, and we can't have that. So I can't plug the 0 right into the function. This is why we have to take the limit as h approaches 0. It's a subtle difference, but it is important to have that difference. In other words, I can't algebraically just plug in 0 for h, although ideally that would work out nice. So whenever we want to take the formal derivative of an object, we're going to focus on the limit of this particular function as h approaches 0. Now the cool thing about having this set up this way and in writing this in function notation is that when we plug in an actual function to this formal definition of a derivative, we'll get the h on the bottom to cancel out every time. So let's clear the screen, let's start over. Let's look at the function y equals 16t squared. So the rock's position is y, t represents time, and so at 0 seconds the position of the rock has fallen 0 feet. Okay? After 1 second, if I plug in 1 second and I evaluate the function, then I will get a different position, and if I evaluate it at 2 seconds, I get a different position. So after 1 second, the position of the rock is 16 feet. Makes sense. After 2 seconds, the position of the rock is 16 times 2 squared, which is 4 times 16, which is 64. Now, if I wanted to find the average speed, what I would do is I would start at the initial position and the final position, and then calculate the average between the two. Remember that time is in seconds and position is in feet. So if I start with the final time, subtract the initial time, I get 2 seconds. If I do the same with the final position and minus the initial position, I get 64 over 2, and that gives me 32 feet per second, which makes sense. In 2 seconds, it travels 64 feet, which is an average of 32 feet per second. However, if I were to graph the function y equals x, or y equals 16t squared, we know that's a parabola. And if we look at the parabola, and I'll draw this real quick, so we have position, which is kind of like y, and t, which is time, which is kind of like x. And if I graph the graph y equals t squared, I'm going to get a parabola. So when t equals 1, if we look at our table of values, then y equals 16. If t equals 2, then y equals 64. And so f of x is equal to x 16x squared if we were to plug this in our calculator. So when we go to graph this function, we know that it's a parabola. And so to find the average velocity of this parabola, what we would do is we would just calculate the distance or the slope between the beginning point and the end point. So my beginning point and the end point is 0, 0, comma, to 2, comma, 64. And if I were to calculate the slope between those 2 points, I would get 32 feet per second. However, if I wanted to calculate the instantaneous velocity when when t equals 2, or exactly at 2 seconds, we know that the rock will be going faster than 32 feet per second. So how do we figure out the instantaneous velocity when t equals 2? Well, what we want to do is arbitrarily choose a distance a little bit away from 2. So we're going to choose 2 points. The first point we'll let t equal 2, and our second point t equal 2 plus h. And then we'll plug it into that equation and take the limit as h approaches 0. So the corresponding values, or y values, would be f of 2 and f of 2 plus h. So if I were to calculate the slope between those two, I'm going to have f of t plus h minus f of t all over h. Again, we can't calculate h. We'd love for h to be close to 0, but if I plug in 0, my equation will be undefined, and mathematically that won't help me at all. So that's why we're going to take the limit of h as h approaches 0. We're going to come in really close to letting h equal 0, and then we'll see some fancy stuff towards the end. So the first part in finding this instantaneous velocity when t equals 2, which is much steeper than the original curve and much steeper than the average, we're going to write the limit of the function. So I'm going to come in and I'm going to take the limit. Let me erase this real quick. And so I'm going to take the limit as h approaches 0 of f of t plus h minus f of t all over h. Well, what was our original function? It was 16t squared. So what I'm going to do is I'm going to rewrite this as the limit of h as h approaches 0 of 16 times the quantity t plus h squared minus 16t squared all over h. And so what I'm going to do now is algebraically kind of expand that binomial and then simplify and see what I get. So t plus h squared is the same as t plus h times t plus h. If I FOIL that out, what I end up with is 16 times the quantity t squared plus 2th plus h squared minus 16t all over h. And don't forget, we're going to take the limit of this as h approaches 0. I can't plug in the 0 because if I plug in the 0, remember the denominator will be 0 and we can't have that. The whole thing will be undefined. So what I'm going to do next is I'm going to distribute the 16 through the parentheses, and that should give me 16t squared plus 32 th plus 16h squared minus 16t squared. Now what we want to remember is that f of t is 16t, f of t plus h is just going to be 16 times t plus h, and that's where that information came from. And we're just expanding it and cleaning it up and seeing if we can simplify and get some sort of answer. With that being said, like I said before, we're just going to push the 16 through the parentheses and see what we get. So that what I should have is 16t squared, right? So I'm going to push that 16 through the parentheses and get 16t squared. And then 16 times 2 is 32, so I get 32th plus 16h squared. Now at this point, we should always double check our work, because what should happen if you're doing this correctly is anything without an h in the term should cancel. In other words, 16t squared will cancel with negative 16t. This will happen every time. So the numerator, when you're done with this step, everything should cancel except for a term that has an h in it. If that's not the case, you made a mistake. The next step would be is to factor out 1h. When I do that, I get h over h, which can be canceled. So by factoring out the h of 32th plus 16h squared, I get the h's to cancel, and now I'm really just taking the limit of 32t plus 16h. Because I no longer have h in the denominator, I could plug in 0 for h, which leaves me with 32t. What does that mean? That means that the instantaneous velocity can be evaluated at 32t, but when are we looking at this? When t equals 2. So the instantaneous velocity at this particular point in time will be 64 feet per second. And that's it. That's all we were trying to do, was find the instantaneous velocity when t equals 2, and we calculated that to be 64 feet per second.